Hello all, welcome to this course on time series modeling and forecasting using R. Okay. Now again this week has been tough slightly because the entire idea of transitioning from a time based approach to a frequency based approach is not that easy, right. So again a strong suggestion, couple of points before we begin with anything new is that if you want more time to sort of revisit all the videos of this week, you should do it, right, because the entire idea about, let's say, spectral density, Fourier transform, inverse Fourier transform, periodogram is entirely new, right. So you might have to revisit some of the technicalities there. I mean, for example, what do you mean by frequency? What do you mean by, let's say, the relationship between e to the power minus I omega t and then let's say sine omega t or cosine omega t. So all these things have to be sort of revised before you enter the last session for this week, which is the practical session. Okay, but just before the practical session, we have one more session today, and here we'll try to sort of wrap up whatever we've been studying this week, and then idea about, let's say, spectral density, estimating the spectral density, and towards the end, of course, I'll show you some examples. Okay, so don't worry. Okay. Now again, where we stopped in the last lecture was we were trying to put forward some non-parametric estimations of S of omega, and one very useful estimator of S of omega is I of omega, which is nothing but called as a periodogram. Okay. And there, what exactly is a periodogram? So periodogram sort of identifies whatever or whichever significant frequencies are there in the underlying signal, and we have some applications of the underlying periodogram as well there. Okay. So now again in this lecture, in today's session, before we begin with anything new, we'll again revisit some non-parametric estimation framework. Okay. So the first idea we'll discuss today is called as smoothing the periodogram. So what do you mean by smoothing the periodogram? So again, the last lecture we saw that periodogram is not consistent, unfortunately, right? We saw that in the last lecture. So again, what do you mean by that very quickly is that the variance does not converge to 0 even if you bring your capital T to go to infinity. So even if you collect more and more observations, the underlying variance does not vanish, which is a bad thing, right? Because there could be some noise which is persistent, and all sorts of disadvantages can occur if the underlying variance does not sort of vanish. Okay. So one solution in that regard is smoothing the periodogram. Okay. So how do you smooth the periodogram to ensure that you are kind of reducing the underlying variance? Okay. So this is exactly the idea, that to reduce variance and obtain a consistent estimator, right, the periodogram is often smoothed by averaging across frequencies. So what I can do is I can look at some of the frequencies, I can average across all those frequencies and put forward a single value. So by averaging across frequencies, I am sort of smoothing out the effect of the overall variance, isn't it? So averaging always smooths out anything. So if you are averaging a bunch of numbers also, you are putting forward a smoothed value comprising of all those values. Okay. Okay, so even inside the smoothing the periodogram section, we have different kinds of smoothing. So the first kind of smoothing is called as kernel smoothing. Now again, this is slightly technical. If you want to ignore the actual technical equations here and the underlying technicalities, you can do it, but the idea should be clear as to what do you mean by kernel smoothing. So kernel smoothing means nothing but one has to apply a weighted moving average. So hopefully you studied what do you mean by weighted moving average long back in some previous week. So we'll again revisit here, right. So the idea is to apply a weighted moving average using a kernel function W. So W is the kernel function, and then we'll apply that to the underlying periodogram through this equation. So S omega hat, so S omega hat means we are trying to estimate that, equals summation small k running from minus capital K to capital K, and then you have the kernel function here, which is W of k, and then I of omega plus k delta omega. So k delta omega, so delta omega is a very small frequency or a small interval. Okay. So using this equation, I can sort of smooth out the underlying periodogram by applying this kernel function. So the extra thing here is that you have a certain summation, you have this periodogram here. So capital I stands for periodogram, by the way, isn't it? So you have the underlying periodogram here, and for each particular value of k, I am attaching this extra kernel function here, and then I am trying to take an average of that. So this is more like a weighted moving average. Can you see that? So this is more like a weighted moving average where weights are nothing but given by the kernel function W. Okay. So in this spirit, what exactly are some of the common kernels that people use? So these all are the common kernels. So the first one is Bartlett kernel. So Bartlett kernel means one has to apply some triangular weights. right. So again, the idea is that if you are changing the kernel, you are essentially changing the underlying weights, or rather the underlying W function. Okay. So the first common kernel is called as Bartlett kernel. The second common kernel is called as Daniell kernel. So Daniell kernel means you are applying a simple moving average. So rather than applying a weighted moving average, I am applying a simple moving average. And third kind of a very famous kernel is called as Parzan kernel. So Parzan kernel means smoother weights for gradual tapering. Okay. So essentially what you are doing is you are kind of smoothing out the weights as you sort of progress down the line. So it should give you a more gradual sort of a tapering towards the end. Make sense? So again, I'll go back to the first slide here. So in order to smooth the periodogram, the first option is kernel smoothing, and then we discussed a few kernels here: Bartlett kernel, Daniell kernel, Parzan kernel, etc. Second approach is directly averaging over bands. So what do you mean by that? So averaging over bands means that divide the frequency range into bands and average the periodogram within each band. Again, divide the frequency range into different bands and average the periodogram within each band. So I'll give you an example. Let's say I sort of graph out the periodogram. This is exactly how the periodogram might look like, and wherever you see peaks here, those are the significant frequencies, for example. So again, on the x-axis you have omega, which is the frequency, right, and then wherever you see peaks, these are the significant frequencies, for example. Now averaging over bands means divide the frequency range into bands. So let's say I divide these into different ranges. So this is my first basket, this is my second basket, this is my third basket, and then this is my last basket. So I'm dividing the overall periodogram structure into 4 bands. And here then what I'll do is I'll simply take the average of the frequencies in each band. So I'll average out these frequencies, these, and then these. So in short, I'm ensuring that I'm kind of smoothing within each band. Okay. So again, the second approach is not very difficult to understand, that you create some baskets of frequencies and then you simply take the average within each basket or within each band. Okay. Now the third important method is Welch's method or Welch's method. So the Welch's method divides the time series into overlapping segments, computes the periodogram for each segment and averages them. So again, a similar idea to how the second point we mentioned just now, where we covered averaging over bands. The only difference here is that, let's say again you have this particular periodogram, right, something like that, and the Welch's method divides the time series into overlapping segments, computes the periodogram for each segment and averages them. So let's say this is P1. So I'll mention P1 here. So what exactly is P1? P1 is the periodogram for the first segment, and similarly this could be P2. So P2 is nothing but the periodogram for the second segment, and so on. So let's say Yt is the underlying time series. I'll divide Yt into some overlapping segments, right? So Yt1, Yt2, Yt3, etc. And for each of those individual overlapping segments, I'll create an individual P or a periodogram. So P1 is the first periodogram for Yt1, P2 is the second periodogram for Yt2, etc. And essentially then what I'll do is I'll take the average of all the periodograms there. Okay. So I'll take the average essentially of all the individual I, k, omega values, let's say, over all k. Hopefully makes sense. And then I think the last equation, if you read the last equation, things would be more clear. I'll come to that part, but this is called as a Welch's method. So the first step is split the time series into overlapping segments. So Yt is the actual time series, you split it into Yt1, Yt2, Yt3, and each segment could be overlapping. Then apply a windowing function. You require some windowing function here. These are some famous windowing functions: Hamming, Han. Okay, again, this is a technical idea. The apply a windowing function to each segment to reduce the edge effects. So since the segments are overlapping, right, there could be some overlapping time series values also. So to reduce the edge effects, wherever you have edges of the segments, you apply the windowing function. And then third step is compute the periodogram for each segment as mentioned before. So P1, P2, P3, etc. And lastly, average over all the periodograms. So I can write down a simple equation like this. So S omega hat is nothing but 1 by capital N summation k going from 1 to n. So let's say you have n segments. Okay, so let's say if you have n segments, and essentially what you're doing is you're taking a simple average of each and every periodogram here. So I, k, omega. So rather than forming one single periodogram which is I omega, I am dividing my time series itself into different baskets which are overlapping, creating a periodogram for each basket and then averaging over all the periodograms. Okay. So essentially the idea is that we are trying to smooth out each and every periodogram just to ensure that the variance is reduced, okay, or we want a more consistent looking estimator. That's all. Now the last slide here before we delve into anything new is a small comparison of estimation techniques, right. So here I think things would be clear, much more clear if you sort of pay some attention to this graph here or this table here. So again the left hand side I am writing down the method. So parametric, periodogram, smooth periodogram, and the last is Welch's method, advantages and disadvantages. So what are the advantages for a parametric method? So smooth, interpretable, efficient for stationary models, but disadvantages is require some correct model specification as discussed even earlier, because if you are proposing a parametric approach, then you would want to put forward a known model, let us say ARMA, ARIMA, etc., right. So this could be a disadvantage, right, that it requires a correct model specification to be put forward. But when it comes to periodogram, so advantage is simple, high resolution. By the way, periodogram is non-parametric, right. But what is a disadvantage? Noisy, inconsistent, we have seen that earlier, and hence a solution is smooth periodogram. So smooth periodogram reduces noise, improves consistency, but one of the disadvantages even after you smooth the periodogram is it may lose some frequency resolution. And lastly, Welch's method, advantages is robust to noise, reduces variance, etc., but one con is reduced frequency resolution due to segmentation. Make sense? So so I think the entire idea about, let us say, whether to go for a parametric approach or whether to go for a non-parametric approach should be clear by looking or analyzing this small table here. Okay. Okay, so now we are almost towards the end of the theory in this week. So we will tie everything down by a final few topics here. Okay, a final few topics. Now some practical considerations in estimation. So the entire last session this week, and then first few minutes of even today's session has been on estimation. Okay. So what exactly are some practical considerations when it comes to estimation? So the first consideration is choice of that windowing or choice of the kernel function, right. So a good window reduces spectral leakage while maintaining frequency resolution. So some popular choices are, let us say, rectangular, so high resolution but suffers from leakage, or Hamming and Hahn. So Hamming and Hahn reduces leakage with moderate resolution loss. So the essential part is to choose an appropriate windowing function, let us say either rectangular or Hamming or Hahn, and to choose an appropriate kernel function. So all these things we mentioned just a short while back, right. So the idea about smoothing a periodogram could be made much more robust by choosing an appropriate windowing function, by choosing an appropriate kernel, etc. Okay. So idea is that one should be able to reduce the spectral leakage as much as possible, and at the same time one should be able to maintain the frequency resolution at a particular level. Okay. And second could be choice of bandwidth. So what do you mean by that? So smoothing bandwidth in kernel smoothing controls the trade-off between variance and resolution. So a smoothing bandwidth controls that trade-off that we talked about in the last session between variance and resolution. So what do you mean by that? If you pick a wider bandwidth, so wider bandwidth means less variance but more smoothing, whereas a narrower bandwidth means more variance but higher resolution. So there is always a trade-off between how do you fix the appropriate bandwidth. So the bandwidth should not be very wide and it should not be very narrow, right. So both the endpoints are kind of cons. So one should manage the bandwidth somewhere in the middle. Okay. So choice of bandwidth is one practical consideration when it comes to non-parametric estimation. And third could be, let us say, handling non-stationarity. So for any non-stationary process, use time frequency methods like, let us say, wavelet transforms, short time Fourier transforms, right. So if you are handling any non-stationary time series, which is, let us say, entirely non-stationary, and then even after differencing it is not coming out to be stationary, then For such situations, you actually have to rely on some time frequency method. So, there is a combination of both time and frequency methods, and these are some underlying techniques. So, wavelets, wavelet transforms, or STFT. So, STFT is called as short time Fourier transform. Okay. And then sampling rate. So, one should always ensure that the sampling frequency, which is Fs, satisfies the Nyquist criterion. So, this is a very famous criterion. This is called as Nyquist criterion. So, what do you mean by Nyquist criterion? That the sampling frequency should be bigger than 2 into f of max. So, f of max is the highest frequency. So, you look at the highest frequency, you multiply that number by 2, and my sampling frequency should be at least that number. Okay. So, ensure that the sampling frequency f of s satisfies the Nyquist criteria. So, Nyquist criteria means that if the sampling frequency, or in general any frequency, exceeds 2 into the maximum frequency, then we are good to go. So, this is called as a Nyquist criteria. Okay. Now, let me again just for a second go back to the previous slide. So, these are some of the practical considerations when it comes to estimation. So, handling non-stationarity, then sampling rate, right, and choice of bandwidth, and the first one was choice of windowing function. So, let us say rectangular or Hamming-Hahn, and then choice of the kernel, so on and so forth. Okay. All right. So, now we come to some practical applications of estimation. So, some practical applications of estimation can be one of all these. So, the first application could be in climate science, right. So, let us say estimating the spectral density of temperature or rainfall time series to study some seasonal and annual cycles. Okay. So, by the way, all these applications or all these practical applications are just to tell you the importance of estimation. So, estimating the SDF or the spectral density. Second application could be in finance. So, let us say detecting the hidden cycles in stock returns or interest rate movements, etc. Third could be in speech processing. So, analyzing voice signals to extract the pitch and the tone of the speech, etc. Or there could be an application in, let us say, vibration analysis. So, estimate the spectral density of vibrations in mechanical systems to identify faults. So, all these could be some practical applications when it comes to studying and analyzing the estimation of the underlying S of omega or the spectral density function. Okay, so now we will focus on one particular example. So, enough of theory about estimation and so on and so forth. So, one particular example, and then things would be slightly slightly more clear. Okay. So, here what we will do is we will consider this time series. So, y t equals sine of 2 pi f1 t plus 0.5 into sine of 2 pi f2 t plus some random error. So, epsilon t is a random error as before, right, and my f1 and f2 are the two frequencies. So, I am fixing my f1 to be 0.1 hertz. So, 0.1 hertz is a low frequency, and at the same time I am fixing my f2 to be slightly higher. So, 0.3 hertz, which is high frequency. Okay. So, my f1 is low frequency, f2 is high frequency, 0.1 hertz and then 0.3 hertz. Epsilon t is a random noise with, let us say, 0 mean. So, we can assume some 0 mean for that. And now what exactly is the goal? So, the task is to compute the periodogram to identify the dominant frequencies f1 and f2. So, we want to compute the underlying periodogram, and periodogram would nothing but estimate the spectral density function, right. So, we want to compute the periodogram to identify the dominant frequencies f1 and f2. Okay. So, how do you do it? So, the first step, so steps in the computation. So, the first step is generating the time series, right. So, you have to generate some data first. So, for that matter, let the sampling rate be delta t equal to 1 second. So, the sampling rate is 1 second and the total time series length, so capital T happens to be 20 seconds. So, these are the observations. So, small t runs from 0, 1, 2, 3, 4 up to 19. Okay. So, in that case my underlying time series becomes nothing but that. So, y t equals sine of 2 pi into 0.1 t because my f1 is 0.1 plus 0.5 into sine of 2 pi into 0.3 t because my f2 is 0.3 plus epsilon t, where t is nothing but this bunch. Make sense? So, you have to fix couple of things beforehand, right. So, f1, f2, delta t. So, my delta t is 1 second. So, the sampling rate is 1 second I will be sampling at each and every second, and how many observations? So, the total time series length capital T is nothing but 20 seconds. Make sense hopefully. Now, the next step is DFT or discrete Fourier transform, right. So, the periodogram is computed from the DFT. So, we have seen this even before in the last session as to how would you construct the periodogram, right. So, the first step is to construct the DFT. So, DFT again using this formula. So, y omega k equals summation small t running from 0 to t minus 1 yt e to the power minus I omega k into t, where my omega k is nothing but this value, which we have already seen in prior session. So, my omega k is nothing but 2 pi k divided by capital T, and k running from 0, 1, 2, 3, 4 up to t minus 1. And lastly, so if you remember this formula from last session, that how do you derive the periodogram from DFT. So, the only thing I have to do is to take the square of DFT and then scale it down by 1 by capital T. So, essentially my periodogram, so I omega k is nothing but 1 by capital T, absolute value of DFT, square of that. Okay. Now, what exactly are the frequencies of interest? So, let us say with the value of capital T to be 20, the frequencies are nothing but small k by t, and then k running from 0, 1, 2, 3, 4 up to capital T by 2, and then these correspond to all these frequencies. So, 0 hertz, 0.05 hertz, 0.1 hertz, 0.15 hertz, all the way up to 0.5 hertz. Okay. Now, again remember one thing. So, why are we only restricting up to capital T by 2? This is because we want to maintain the Nyquist criteria. So, if you remember, the Nyquist criteria was what? So, Nyquist criteria was that we can actually only take up those frequencies which are halfway, up to the halfway. So, we only want to restrict ourselves to values of k running from 0, 1, 2, 3, 4 up to capital T by 2 only, and this is the bunch of all the frequencies. And last step is compute the periodogram. So, compute I of fk for each value of fk. Okay. So, again if you want, I can re-summarize or sort of summarize all the steps, right. Let me go back very quickly. So, the first step is obviously generating the time series, generating the data by fixing the sampling rate to be 1 second in this case, and then capital T, which is 20 seconds. So, my small t automatically becomes 0, 1, 2, 3, 4 up to 19, and this is the underlying time series that we have. It has two sinusoidal components. So, sine of 2 pi into 0.1 t and 0.5 into sine of 2 pi into 0.3 t plus the random error. Then the next step is to create or derive the DFT. So, DFT could be derived using the regular formula, and once you have the DFT, I can find out the power at each frequency using this formula by rescaling by 1 by t, taking the square of DFT, etc. And lastly, we have to identify the frequencies of interest. So, frequencies of interest is nothing but fk equal to small k by capital T, and I am only restricting myself to 0, 1, 2, 3, 4 up to t by 2, which translates into all these frequencies. And last step is, for each and every frequency in this set, I have to compute the underlying periodogram. So, compute I of fk for each fk in the above set. Okay. So, hopefully the steps are clear as to how do you find out the periodogram if you are given with a set of frequencies. Okay. So, in the same spirit, we will try to find out some frequencies manually. So, manual computation of a few frequencies. So, let us compute the periodogram for, let us say, f1 to be 0.1 hertz and f2 to be 0.3 hertz. Okay. So, this is exactly how the Fourier transform coefficients would look like. So, at f1 equal to 0.1, I can immediately put in the equation that we saw earlier, and then y of 0.1 happens to be this guy, and at f2, which is 0.3, my y of 0.3 happens to be this guy. Okay. So, this is the calculation of DFT, by the way. So, I am deriving the DFT at those frequencies, which is 0.1 and 0.3, and once you have that, I can use the power spectrum equation for finding I at 0.1 and then I at 0.3 by using the earlier equation. So, you rescale it by 1 by capital T, you take the square of DFT, etc. So, I at 0.1 happens to be this, I at 0.3 happens to be that. Okay. Now, the very last section we will discuss in this entire week, of course, in the theory session, is an idea called as cross spectrum. So, what do you mean by cross spectrum? So, one can actually extend from one series to two series. So, let us say xt and yt be two stationary time series processes, each with mean 0. Then the following immediate questions could be asked. The first question is, are there periodicities related to each other? So, are there some fluctuations or periodicities related to both the series xt and yt, and if yes, what is the phase relationship between them? So, at the end of the day, the questions which one can ask is that, is there any frequency sort of a relationship between xt and yt? Okay. So, for this we will require the idea of cross covariance. So, I think we studied cross covariance long back in one of the earlier weeks. By the way, cross covariance is nothing but this covariance between xt and some lag of the other series, let us say yt. So, yt minus t. Okay. So, for creating this idea about cross spectrum, we require some idea about the cross covariance. And again, the moment we have the idea about cross covariance, we can again do the entire same thing. The only difference is, rather than focusing on one series, we are transitioning to two series, which is xt and yt. So, first step is to create the Fourier transform. So, Fourier transform in this case is called as cross spectrum. So, Fourier transform of the cross spectrum is given by f x y omega and then summation e to the power minus I k omega. The only difference is, here we have the cross covariance. Okay. And here we can use some properties. So, for example, spectrum of a sum. So, using the cross spectrums, we can compute the spectrum of a sum, and one can actually simplify further, right. And then here, if you try to simplify and put forward some assumptions, I can actually sum them up. So, if xt and yt are uncorrelated, it so happens that f of z omega happens to be nothing but the sum of the individual Fourier transform. So, f of x omega plus f of y omega. Okay. So, this whole idea is about cross spectrum. So, again, obviously technical, but I thought of putting it here as to it might be a situation that, rather than focusing from a frequency domain approach on a single series, can we sort of bring in the idea of multiple series, let us say xt and yt. Okay. Now, the last slide is some few practical examples of cross spectrum. So, let us say identifying the leading and lagging relationships between, let us say, GDP growth and stock market returns, to understand which variable influences the other and at what frequency. So, if you notice here, there is sort of a commonality between GDP growth and stock market returns, and we want to identify the significant frequencies underlying the relationship between these two variables. Okay. So, probably the first application could be portfolio diversification. So, understanding how asset returns such as stocks and bonds co-move at short or long term frequencies, and the second could be, let us say, forex and commodities. So, investigating the relationship between exchange rates and commodity prices to, let us say, model some hedging strategies. Okay. So, whenever you want to focus on multiple series, we have a thing called as cross spectrum, right. So, one has to analyze the both the series together from a frequency based approach. All right. So, hopefully again a small disclaimer towards the end, that almost all the ideas here are completely new from what we have been studying so far in this course. So, you might want to revisit all the videos, some of the technical terminologies here, might want to revisit some of the textbooks which are given, right, and sort of build your understanding about the entire idea about frequency domain approach before we enter the very last session in this week, which is a practical session. Okay. Thank you.